euros or 500. There was a meeting that I had to be part of that started at 9 o'clock and it's going on until 10. And so I came at 9 o'clock and set this up and I was walking around outside. And then they called me for the vote. And I just took the vote and ran and then I was talking and then Andrew reminded me that I have not done. It's not about Donald Trump's government, so it's not that big, but you know, probably you don't want it to be public. Anyway, I forgot to link the slides unfortunately, but there is no simple way I can do it here. So right after the class, I will link it. I'm sorry about that. So what I am going to do today, as I said, is go from the game research to Markov decision processes. And when we are making that shift, all sorts of interesting things happen at once. And so it's kind of useful to have a sense of how much of the ground shifted under your feet. Okay? So I might go a little slower, but on the other hand, I want to go faster than I've been going, so we'll see what happens. Anyway, so on last week, after Wednesday, I was in the Computation Museum for the panel, and then so they gave us like a special behind the scenes, like a person guided tour of the museum, and it was interesting that this, of course, is Deep Blue, a part of it at any rate. So Computation Museum has Deep Blue, and this is, of course, the Deep Blue team. So it was kind of interesting that I was just talking about Deep Blue in the class, and I got to see a piece of the real Deep Blue up there. If you remember, I mentioned before leaving in that class that between DeepMind's AlphaGo and IBM's Deep Blue, one for chess and one for Go, at the time of 1997, the focus was on faster search and taking whatever is a reasonable evaluation function has been found by the experts. But unfortunately, experts are not particularly good at saying what is the best way to compute an evaluation function. Now, when you try to compute an evaluation function, it would be of the type that I mentioned for the tic-tac-toe, which is, for example, number of rows, columns, diagonals open to max minus number of rows, columns, diagonals open to min. Those are easy to compute. For example, the kind of chess simplistic evaluation functions for chess, even from my standards, which are actually adequately awfully low because I'm not a chess player, is, for example, number of queens that are still left on the board. Okay, it is a feature, right? I'm assuming that if you have fewer queens, there's only one queen, and if it's dead, then it's not good. And then, of course, number of kings left on the board is even greater feature. So if you have 0 kings, then pretty much you're done. Okay, and then of course the question, of course, is things like knight power and things like bishop power and things like pawn power. And people did try also in those days to look at. So this is again 1997. It's hard for many of you. How many of you were even born by 1997? Okay, what were you doing? So in 1997, I don't know where you were after having been born, but there wasn't really that much of a big internet. I mean, web, for example, internet was there for a long time, but web wasn't really big. And so, in fact, people used to print books on chess endgame positions and the chess opening moves. Okay. So an endgame position in chess, once again, I'm saying this as a non-chess player, so you should take it with, 3 spoons of salt. An endgame position is if you get to a certain configuration of the board, then in essence, there is a way of winning the game, no matter what the opponent does. Okay, it may not be the next move. It may actually be 4 moves away. It may actually be 10 moves away. I don't know how many of you have taken my suggestion and watched Searching for Bobby Fischer, where in the last game, basically this guy is able to see a 12 move away, certain way. Okay, that's basically the kind of thing that we're looking for. So people are not always able to see it, but for certain standard positions, people have figured out that if you get to that position, then pretty much you are home free. Okay, and so those are called the end game positions. And so one question would be, can you, and of course you can make, having reached the end game position, if you don't know what are the moves you are supposed to make, and if you make stupid moves, you the max guy makes stupid moves, you can always lose. Okay, the only point is the value of that end game position is so high that if you do the optimal action from then onwards, you're guaranteed to win. By the way, this word value will come up again in MDPs with exactly the same meaning. That the value of a state is the best you can do starting from that state, assuming you have brains to do the optimal actions. Okay? So you can be in a state which has a high value and still lose in life because you continue to do inoptimal actions at every point of time. But if you are in a low value state, however optimal your actions are, there is probably very less likelihood that you will succeed. Okay. Anyway, so endgame positions, for example, there used to be books on endgame positions, and one of the things they did was code up these endgame positions and then use that as part of the evaluation function, for example. And if you ever reach an endgame position, I mean, if Deep Blue ever reaches an endgame position, it will just make those moves. How many of you actually have seen the Bobby Fischer last part? I don't know why I waste my time telling you to do this, but you can at least go and see the ending scene. Essentially, it's the one place where chess becomes more like an actual Sunday daytime football, I guess, because it's like suddenly the moves are like very fast, even though it's a championship game. Because in fact, this kid knows exactly the optimal moves to make from there onwards, and it's pretty much clear cut for him. Okay. Normally, if you don't know, then you have to do that search, that min-max search at every point of time. So you can take the same amount of time every time. Okay. So this computation of endgame positions, for example, they use that, but mostly that's about it. The evaluation functions were really, they didn't put that much effort into evaluation functions. They put a lot more effort into search, speedy search, and that's where this guy comes. Okay, they actually built a separate machine, a special purpose machine with VLSI chips, whose whole purpose in life is to spit out chess game positions. Okay, so that, remember, the cost of any search is the child generator function. That's why we count the number of expansions of a node. It's the same for min-max search. The number of times you take a board position and generate all the children board positions. That's where you spend time. And if there is a special purpose architecture that just spits out, those game positions are there. Now, all of this is a long-winded way of saying that if you were to go to AlphaGo, if in fact the MISA service were to try and put AlphaGo machine, quote unquote, in some place, there is never going to be any such machine. Okay. First of all, of course, they did have the cluster of computers, the GPUs, etc., that they were using for training their value function learning neural network. But much more than that, the very important thing was these billions of code games that they could actually train themselves on. Okay, in the old days, there was no such thing. In fact, in the 97 time frame, there weren't that many online chess games that are available. So in fact, this raises an interesting question, which actually is when Deep Blue won, people agreed that Deep Blue won, but they also tried to argue that that's cheating. In some sense, that's not the way people play chess. People see patterns in the board, and grandmasters are able to see patterns in the board and are able to see what's going to happen much before they get to the final position, and they're not doing this quote-unquote brute force search in their heads. Now, there's an interesting discussion, an argument that can be had as to how do people know what they're doing in their heads. Do you know what you're doing? And in fact, one of these most useful things to have in mind is introspection is the worst form of psychology as well as cognitive science. Asking yourself, how do I do it? Oh, well, I'm sure that's the way the program is supposed to do, is not exactly good for some of these things like finding patterns and so on. And so you don't necessarily know whether people are actually doing brute force search. And people always are extremely good at trying to say that they had a genius inspiration. So I don't know, I'm sure you have some friends of yours that you hate with all your guts because they are actually doing well in all the exams and that you're not doing well. And if you ask them, how do you do well in the exams? They don't say, no, I have no life, I just sit at home, study, I don't go to movies, I don't see TV, I don't have boyfriend, girlfriend, nothing. That's how I do well. They don't say that. If they say that, actually you'll feel good. At least you'll say, they don't have life, I don't have great. I'm fine. But instead what they say is, oh, it's easy, I see patterns. I'm a genius. Okay, humans are extremely good at making themselves look as if there is no actual work involved in many, many things. And in fact, this has very interesting sociological side effects. For example, in fact, this is a digression, but I was just reading this article about in fields where people think that it requires a genius to do well, minorities and women don't take part as much in those fields. Now, if you go into those fields and actually see whether it requires genius or whether it requires real hard work, you'll see pretty much everything requires hard work first. But we'll never say that. And in fact, there's a sociological research showing that maybe we should come out and tell the way it is so that new people can come into fields without prejudging themselves, saying, oh, hi, compared to this guy, apparently he's watching movies and everything and still getting good grades. I'm not that much of a genius, so maybe I should go into this field. But that guy probably has no life. Behind your back, he or she is essentially spending all their time doing hard work. Okay? So that comes back to this chess issue of we don't really know how grandmasters actually do well. They may very well be doing brute force search. But that was the argument that was given as a counter-argument in 97. But now that we have AlphaGo, in fact, we can do a new version of Deep Blue now. Because just as you have millions of Go games on the web, there are even more millions of chess games on the web. So you can actually apply the same ideas to chess and see if in fact, if that particular machine conforms better to your intuitions of native genius. You understand what I'm saying? So in some sense, partly the native genius versus brute force search in the context of min-max search is having a good evaluation function that you learned over a long period of time. Versus at that point of time doing brute force computation of multiply search, multiple levels deep search. At the time of chess of Deep Blue in 97, we didn't have the ability to learn these evaluation functions automatically. Eventually, you need both search and evaluation function, and AlphaGo does both. But chess obviously just mostly went with very fast search. Okay, so that's the reason why you have that particular machine out there. Okay, the other thing I want to mention about games before I go forward is, so we talked about the fact that normal min-max search goes all the way until leaf nodes are either probable, wins, losses, or draws. And we also talked about the fact that actually for real games like chess, in fact you can't go all the way because it will be too deep, and in fact you would spend all your time just computing one move. Okay, so what you do instead is, of course, where you basically go some levels deep and then essentially apply the evaluation function there and act as if evaluation function is the real value of the board and then back it up using min-max data. Okay, so now the interesting question, of course, is how deep do you go? You understand what I'm saying? So you don't know how far you are supposed to go and before you reach the level where everything is a definite win, draw, or loss. So you have to just go up to levels deep. So one question, of course, is how deep do you go? And second question is it possible that if you go deeper, your backup will be better? You understand what I just said? Okay, so you clearly know that if you go all the way to the place in each branch where the final board position is a definite win, loss, or draw, and you back up from there, that is the best min-max evaluation you can ever do. And that, you cannot win over that. You can only, basically, if you do full min-max search, then your opponent can't beat you unless the game is rigged and that you are anyway going to lose to begin with. Do you see what I'm saying? Okay. Then the question, of course, is we know that the deepest, that's the deepest, and if you go there, you will be getting the best quality move. Now, you don't have that much time, so you want to go a few fly deep and then back up. The question is, how many fly deep? Now, the interesting thing, there are two issues here. One is, how do you think the value of the accuracy of the move changes as you go deeper? The more obvious thing is that it's somehow monotonic. That means the accuracy keeps increasing as you go deeper and deeper. But you don't know. Maybe it's possible that the accuracy kind of goes up, comes down, goes up, comes down, goes up, comes down, and finally goes up. It could be non-monotonic. In fact, you could build games, it turns out, which have this notion of game tree pathology, where the deeper you go, the worse you get. The deeper you go, the worse you get in terms of the accuracy of the move, except when you go all the way to the full deep move. So those things exist. Okay, so then this raises the question of, first of all, why does going deeper increase accuracy? Which is the next slide I'm going to talk about. And secondly, how much deeper do you want to go? And in general, the answer for that is, given that I'm going to show in a minute that the deeper is better in general, you would like to go as deep as you can before it's your time to make a move. And if you don't have a good understanding of how deep you should go, then you might actually, let's say, go 3 deep, find the move, keep it somewhere. If it's still not your time, go now 5 deep. Find a move again. And the 5 deep move is better move than the 3 deep. If you still have more time, then go 7 deep. Find the move. If in the middle of while you are doing the 7 deep computation, they say time is up, you have to make your move. Then what do? You take the 5 deep move and then put it up. This sort of a decision-making algorithm these are called online decision-making algorithms. Write it down, online decision-making. In general, in computer science, you assume that computation is all mostly offline. When you talked about a sorting algorithm's complexity, you only care about how long does it take before it ends. There is no such thing as, if I stop it in the middle, how good is the sorting algorithm going to be? What is the output going to be like? This approach that I told you, which is start with a initial depth and then keep going deeper and deeper while keeping the best current value, that is an online algorithm. And it is something where you can come up with the best solution you can, given the amount of time you have, even if you don't know how much time the computation is going to take. And this is kind of important because in an intelligent agent's life, The total time is the time for thinking plus the time for acting. Imagine I'm standing in the middle of rural road right now, and I see cars coming both directions, and I'm trying to come up with the best way of dodging the cars to go to the other side. And it turns out that in fact MDP policies could help. And in fact, you may even have to deal with Markov games if you think those guys are out to get you. It's not just nature, the people driving the cars are out to get you, they're trying to kill you. In which case you have to come up with a better strategy. But either way, you can come up with an optimal policy. Maybe the optimal policy takes 3 hours. At which point of time you are already part of the road because somebody has run you over. Do you see what I'm saying? Because the time for thinking doesn't come out of nowhere. The time for thinking comes out of the total time. This is the kind of thing people do for timed exams, right? You assume that you come to the exam without sometimes studying. Yeah, I can figure it out. I can look at the problem and sort of reason from first principles. Unfortunately, that's not going to work in a timed exam because we are checking whether in fact you have enough of an understanding that you can very quickly come up with the answer. The amount of time you spend thinking about how to come up with the answer is going to be counted against you because time is over by the time. I'm sure you all had this. I mean, there's some exam, some particular question that you try to do it for first principles, and that was the only thing you completed, and the exam was over. Which is why I tell my students, especially when I set exams, do the following online or anytime computation. What's an anytime computation? Basically, in an exam scenario, answer all the easy questions that you know answers to, and then start spending time on questions that you have to come up with first principles answers. Most of you who have taken exams in your life know this is the reasonable thing to do. And yet, somehow people think, maybe because of the GRE and SAT or something, they think that Rao would have set the exam such that first question is the easiest, second is the next easiest, third is the next easiest, and the end will be the hardest question. Do I look like that kind of a person? I may very well put the hardest question as the number 1 question. So I ask, quickly look at the entire exam, find out the ones that you know, answer them, and then spend time, answering the hard one. That's an anytime algorithm. Okay? In general, anytime computations are ones where the quality improves as time goes on. And so basically, it's not just the case that normal computations are all or nothing computations. You stop the computation, like 3 microseconds before it's going to be done, you'll get garbage. An anytime computation, on the other hand, tries to give you accuracy that keeps increasing, and if you wait until it's completely done, maybe it'll give you the best accuracy. But otherwise, it still gives you some accuracy. So, min-max with limited depth is a very interesting type of a problem. It's called online search problem. It's an online search problem. Okay, it's very important thing to keep in mind. So that's all is written here. And one interesting thing is to understand that imagine I give you a game which has been solved, and it's been proved that Max can't lose that game. You understand what I said? And if you play full min-max on that game, you too, and if you are the max for that game, you will win too. If you don't play full min-max, if you do depth limited cutoff, you could lose the game that has been solved to be winnable to you. Do you understand what I'm saying? It's the same thing. I could have set up an exam which is actually doable for you in 1.5 hours if you picked it in the right direction, but then you decided to pick it in the wrong direction and you basically stop with one question. Okay, so it is important to understand that online search algorithms are not guaranteed to be optimal. In fact, if an agent is actually making moves based on online search, it could paint itself into a corner, or it can fall off a cliff. in real life. That means it can die. And the question for that is, how do I know? So of course, it's one thing losing games, the other thing dying. Right? Dying, we probably don't want our agents to die. Okay? So the question is, how do I know that I'm in a world where essentially online search is not going to kill me? And one way is, if you go to the wrong place, you can always come back to the right place from there. Imagine death is reversible. Then it won't be death. It won't be dramatic anymore. The only thing that's interesting about death is it's irreversible, as of now. Okay? So if you are in a state where you are dead, from there you can't reach any other state. Unless, of course, you are into some quasi-religion, there's a whole entire set of virtual states you can reach, but none of my states you are able to reach. You see what I'm saying? Okay? So the death state makes the environment have this property that there are states of the environment, once you get in, you can't get out. More generally, you call an environment to be, this is the thing that you can impress your friends, ergodic. An environment is ergodic if there is non-zero probability that you can go from any state to any other state, if you touch. Real world is not ergodic because of the death states. You see what I'm saying? Okay, so online searches are great for non-ergodic, great for ergodic domains. Okay, and another very interesting thing that comes in this scenario is sometimes the world itself is not ergodic. But we want to stabilize the world such that our little kids can live. So imagine you have a little kid and in your living room and you happen to have some hand grenades and handguns and some huge big, ditches in the room, and you hope for the best for the kid. I hope the kid knows what the kid is doing. It's true that kid is only 1 year old, but I hope they have some intelligence. Obviously, you won't have any kids left in that case. World at large is very hard. You can actually fall into traps, you can get shot and all that stuff. But why does that have to happen in your living room? So what do? We stabilize our living rooms if we have any sense. Those of us who don't have sense will also leave a few guns here and a few ditches around, and then see if the kids can still get by. Sometimes they get by, maybe because there is law of probabilities. And sometimes they'll fall in the ditch and can't come out. And you can then say at least that, well, the kid should have learned because the world is, is non-ergodic. My living room is part of the world. So it too is non-ergodic. You see what I'm saying? So we actually live in this big bad world which is non-ergodic by making pieces of the world which are ergodic. Locally. You see what I'm saying? It's very hard to focus on what I'm saying if we are having this discussion in the middle of a forest where tigers can come and eat you. So we made sure that we close the doors, no tigers are being allowed in, and so you can focus on what I'm saying. So I stabilize this world. We all do. Okay? That's the kind of thing that you have to understand about ergodicity and how we stabilize the world so that they have these properties. By the way, ergodicity is a great property that we didn't talk about before, but it's very important. Okay, the other thing that I want to mention is why is deeper better, which is going deeper in the min-max search tree. Why is it better? I said it's sort of better. It looks kind of reasonable because all the solutions are at the very end. So, and if we go there, we'll get the perfect accuracy. So maybe if you go deeper and deeper towards the goal, maybe you get better and better. But that's not obvious. So what could be the possible reasons? Under what models are going deeper actually better? One answer is, possible answer is that if you notice that instead of going all the way deeper, you could actually just do the following thing. Imagine if there's a big tree like this. So I have, there's there's 4 moves here, right, in the very top level. I could just apply the evaluation function to my moves directly. Do you see what I'm saying? No min-max at all. So Max basically looks at the 15 moves she has and then applies the evaluation function to the board positions at those 15 moves. That's basically one depth. You see what I'm saying? Okay? So if you do that, you will actually get a solution. So you will say, okay, fine, based on that, I have to go this way. So why do you think this is not right, but if you go up to here and do the same evaluation here, and then back it up using mins and maxes, somehow you will get better? Why do you think that is going to happen? You just assume it will happen, what the heck. People seem to believe that, I think it will be true. But why do you think it will happen? One idea might be that if you just take mins and maxes of that, there is no mins and maxes here at all, so you just apply the evaluation function. Here you apply the evaluation here and back up using mins max all the way. So if there's going to be some magic happening, it has to be either because taking the evaluation at the lower level and combining those by mins and maxes increases the overall accuracy. Somehow, these aggregated values of these lower level nodes then come upstairs. Notice, for example, that that particular guy has a subtree below it, right? And so it actually has 2 values. One value that you just gave it when you are at this level. Another value you gave it by coming here, backing it up. So there are 2 different values for the same node. You see what I'm saying? Which value is better? Deeper basically means the value that you get by doing this backup is somehow better. The question is why? And the reason could be that somehow doing the mins and maxes improves the quality, or that going deeper somehow makes the evaluation function itself better. Oftentimes, evaluation functions by themselves are basically the same set. So, for example, in the tic-tac-toe, it's the number of rows, columns, diagonals open for me minus those open for my opponent. And you can apply it here or apply it here. There's no real reason to believe that somehow it became more accurate here than it is here. And then if you believe that taking mins and maxes of quantities is better, then that's what's called a cardinal Sinon statistic.